Okay, over the next 2 days, we are going to talk about the topic of inverse functions. Inverse functions, if you think about just the word inverse outside of the world of math, inverse means undoing something or opposites of each other. And that's what inverse functions are, is they are opposites of each other. If you were to think about a graph, opposites of each other maybe being like the x's and the y's, right? And that's where we focus a lot of our time on when we're looking at inverses, is flip-flopping our x's and y's. And like I said, not on your note sheet yet, but if you look at this, this is a very basic example and kind of an intro to inverse functions. If I were to look at this graph, 3x minus 2 and y equals mx plus b, that would start at negative 2, have a slope of 3 over 1, so up 3 over 1, up 3 over 1, and it would be a line that looks like this, okay? Well, one of the processes, and we're going to talk about this a little bit more tomorrow, but to graph an inverse, we just take all of these nice pretty points that I put out here, and we take them all and we turn them upside down. Is that I have this point 0, negative 2, 1, 1, and 2, 4, and to do an inverse, I will just exchange the x's and y's. Turn that point backwards, and it would be negative 2, comma 0, or this dot over here. Now, sometimes you will notice that when we do an inverse of an individual point, or even of an entire function, is that it ends up being the same thing. If I turn the point 1, 1 around, it's still 1, 1. That point is its own inverse, okay? And then I can do the last one here, turn that around, it'd be 4, comma 2, and that green line would represent the inverse of the blue. And what you'll notice is inverses reflect over a certain line, and that is that line that cuts our picture diagonally in half, called y equals x. If I were to draw this y equals x, do you see how it runs straight through the middle of those two? And if I were to like fold my picture in half on that line, that they would match up exactly with each other, okay? That's where we see inverse functions, is it's a reflection over that line. We don't spend a lot of time talking about that, but it's true, and I just wanted to show you visually what's going on. So not every function has an inverse function. So that's where we kind of start our process today, is deciding which ones even have an inverse to look at. We use this thing called the horizontal line test. Now that phrase might sound familiar because we've used line test before, but it was earlier called the vertical line test. Do you remember that phrase, the vertical line test? We use the vertical line test to see if something was a function at all, right? And if it was a function, it passes vertical line test, meaning it would only hit my function at one point. Well, the horizontal line test identifies if we have an inverse function. The notation for an inverse function is f raised to the negative 1. And what the horizontal line test says is if I draw these horizontal lines through my picture, like there's one, here's one, here's one, here's one, here's one. If I draw these horizontal lines through my picture, that I would only ever hit my picture one time. Now, let's talk about this part right here. Does it look like if I drew a horizontal line down here, it would hit my picture at more than one point? It kind of does, doesn't it? And so what happens in a graph is it's moving so slowly that it almost looks like a horizontal line. But this line, if I were to follow this to the left, it would continue to decrease and decrease and decrease super slowly, but it's heading down forever, okay? And we're going to look at a couple instances where it looks like it might be horizontal that I can clearly tell you that it is not. If I were to follow that function, my y values would keep getting smaller that direction. That picture actually does pass your horizontal line test. I want to show you an example of one that does not. X squared plus 3, if we were to think about what this is, that's a parabola moved up 3, right? If I were to graph that and then take each of these nice pretty points and flip-flop the x's and y's, the resulting picture would look like that, okay? Now, it's not that I can't flip the x's and y's and redraw the picture. I can do that. But the question is the inverse of it a function? Do we get an inverse function? Well, this fails our vertical line test. That's not a function because this fails the horizontal line test, and that's the whole point of the horizontal line test. Today, if we do this and I hit my graph at more than one point, we don't have an inverse function. We just stop because we're not going to go find something that doesn't exist. If it doesn't have an inverse, we stop and move on. If it does have an inverse, today we're going to go figure out what that function is. Okay, so that's the whole point of this inverse function test. So if you will grab your calculators, we're going to start with this first function. Graph the function using your graphing calculator and apply the horizontal line test to determine whether it has an inverse function or not. Our answer will be just yes or no. So this is kind of the first step in our final process here, is just does it have an inverse function? So type that into your calculators. I think a Zoom 6 window should work okay for us here. Use your horizontal line test. Does an inverse function exist? Okay, we should be seeing a picture something like that showing up on our calculator, right? And I try my horizontal line test, hits my graph at more than one point here and here. So because it hits at more than one point, it fails. So the answer, yes or no, is no. There is no inverse function to the one that was handed to us. Okay. The second one that I have up here has a particular place that we need to talk about. So if you will graph this next one, zoom in really close on it, and see if you can identify the little point on that graph that I think could be like up for debate. Okay, so we should have been seeing this picture. Is that the one you guys saw? Do you see the little part that I'm looking at that's questionable? Does it actually pass our horizontal line test? This part right there, right? Questionable, isn't it? I will tell you right now that no, they're not trying to trick us ever, okay? What's happening is our graph is increasing. It slows down, but it's still increasing right there. If you were to put your little bug on your picture and just trace along there, you would see that your y values continue to go up a little bit as you go over that little spot. They're not going to try to trick you with something like that, okay? That will pass our horizontal line test. It would actually only hit our graph at one place. If they want it to fail the horizontal line test, they will clearly make it look something like that, which would fail, right? So this one we would say, yes, it passes. And there's a couple ones that are going to look like that, like the one we looked at earlier. Here too is continuing to increase during that section, also passes our horizontal line test, okay? It will very clearly not if they don't want it to. All right. So now we know how to use that to decide yes or no it has a function. Moving on with that, why do we use it? Because that's step number one in our process of finding an inverse. So the steps to finding an inverse, I have a very basic function as an example. Example, f of x equals x plus 4. Job number one is what we just learned how to do. Determine if the function has an inverse. In order to determine if the function has an inverse, we are going to graph it and use the horizontal line test. Okay, that's what we just practiced on the last page. So that's step number one. If it fails that step, if we say no, you're done. Move on to the next problem. But if you say yes, it has an inverse, you continue on with the next steps. Our next step after we graph it, so this one would graph and look something like that, passes our horizontal line test, so we would say yes, it has an inverse. So we would move on to step number two, and step number two says switch x and y. And so what I'm going to do is I'm going to go down my equation, and every place it has a letter, I'm going to make it the opposite letter. So I'm going to turn all my x's into y's and all my y's into x's. Right now, my function does not have a y. Where is it? It literally doesn't have the letter y in it, does it? It's f of x. Okay, don't be confused by that. Remember that f of x and y are the same thing. So that I could look at this equation as y equals x plus 4, and that might make this next step a little bit easier to look at if I think of it as y equals x plus 4, because now I'm going to go down that equation and every y becomes an x, and every x becomes a y. That's what this step means to do, is just rewrite the equation, switch all the letters. Next step, solve for y. I picked a very basic example for this one, so there's not a lot to do to solve for y. That's what we're going to kind of look at in the next couple ones, a little bit more complex algebra. On this one, we would have literally one step, and that is to subtract 4 to the other side. And my inverse function would be x minus 4. You can write it as y equals. If you write it as f of x, you actually need to show that it is the inverse function, f prime, or sorry, f raised to the negative 1. I don't care if you write it as y equals or inverse of x, f. The last step is state any restrictions on the domain. This should go unsaid for all of it. If we ever have a restriction on our domain, we're always going to have to say what that is. So if it's ever a fraction, if it's ever a radical, if it's ever a radical in the bottom of our fraction, we have to comment on the domain, okay? We don't have a restriction on this domain. It's not a fraction, radical, radical in the bottom of a fraction, so we don't have to say anything. It works for all x's. Any questions on the steps? Okay, let's put those into action. Determine whether f has an inverse function, given f of x equals 2 square root of x minus 1. That first phrase, determine whether it has an inverse function. That says graph it and use your horizontal line test. Okay, so right now we're looking at the graph of 2 square root of x minus 1. And that tells me whether I even need to move on to the next step. If it does pass that horizontal line test, we're going to find the inverse. If it doesn't, we just move on and say it doesn't have an inverse. You guys have calculators, so you could type it in right now. Continuing to practice for our test next week, you actually probably could graph this one without a calculator because that's one of our parent functions, stretched vertically by 2 and moved to the right 1, right? Recognize all those transformations? Okay, so it's going to look something like this. So the first question is, does it have an inverse? Does it pass that horizontal line test? Yeah, I can draw horizontal lines through that. I will never hit it at more than 1 point. It has an inverse. So yes, this has an inverse. So step 2, rewrite our equation. Remember, this is y. And change all of the letters. So it will now say x equals 2 square root of y minus 1. And then I have to just do my reverse order of operations to solve for y. Okay, this is probably one of the most common types of problems that people will make mistakes on, and that is where we have a square root. Just remember that anything under a square root cannot be touched, we cannot undo anything under a square root until we get rid of that symbol. And I can't get rid of that symbol until I get rid of everything outside of that symbol. So start on the outside, get rid of the symbol, and then move to the inside stuff. So the very first thing we need to get rid of on this one, 2, right? Do the opposite. It's 2 times the radical. I would divide by 2 or multiply by a half or divide by 2. It doesn't matter. It's the same thing, right? So you can write that as 1/2 x or x over 2. Same thing. Still cannot do anything with what's under the radical if that symbol is still there. So we got to get rid of that symbol. How do I undo a square root? Square it. This next part right here, when I square the other side, right? Because everything we do, we have to do to both sides of our equation. When you're squaring a fraction, remember you are squaring the whole thing, so we have to square both parts. If there's a number in there, actually write what that is squared. So x squared is x squared. 2 squared is 4. Don't leave it as 2 squared. Go ahead and simplify it out to whatever number that actually is. And then squaring and square rooting are opposites of each other. I would be left with y minus 1 on the other side. Last step, get that y by itself by adding 1 to both sides. I don't care if you get a common denominator or not at this point. We can write it as x squared over 4 plus 1. Or, if you got a common denominator, it would have been x squared plus 4 over 4. Last step is just making sure that we check for a domain restriction. Now, as I go through my list, is it a fraction? Is it a radical? Is it a radical in the bottom of a fraction? It is a fraction, but is there a domain restriction from this fraction? Look at the bottom of that fraction. That's where the issue could be, right? Is the bottom of our fraction ever going to equal 0? No, because it's the number 4 and that's never going to change, right? So no domain restriction on this one because the bottom doesn't have a variable in it. This, it should look like this. Oh, that's a great question. I am so glad you asked that. Yes. Yeah, it does. Because the only ones we are using is from the inverse of this. Well, that is just this. So actually the domain of this comes from the range of the original function. Well, the range of the original function is 0 up to infinity, which makes our domain actually 0 up to infinity. So it's only going to graph the second half of that. We don't need to worry about listing that as a domain restriction because it's not a restriction, it's just the domain that would show up if you were to graph by doing point by point instead of typing it into our calculator. Yeah, good question. Other questions? Okay. This next one is probably algebraically the most challenging as far as finding an inverse. So I would make sure that we put good notes for ourselves off to the side as to the step-by-steps we do. You're going to see this one show up probably at least on every assignment and assessment we do. There will be one of these fraction types. Okay. Now with that being said, I've probably answered the first part for us. Determine whether it has an inverse, but I think it's very important for you to look at the graph of this one. So go ahead and graph this one real quick, because there's something I want to point out and tell you why it passes our horizontal line test. Make sure you know how to type in a fraction. At the end of the next chapter, we're actually going to learn a lot about rational functions, what these graphs look like, how we can dissect each part of the graph, all of that. But right now we're going to rely on our calculators. And so if I type this in, now it's pretty small. So if you zoomed in bigger than your standard window, the 10 by 10, it's a little bit easier to see. But if I zoom in, it kind of looks something like this. Okay. Does that resemble something on your calculator? Yours probably looks a little bit smaller because this is happening at a half and this is happening at a half. So it's really small on your calculator. So you can make your window smaller and it'll blow that up a little bit more to look like this. But the question is, does it pass a horizontal line test? Now, in a rational function, a lot of times we're going to have this thing called a horizontal tangent, or sorry, a horizontal asymptote that's running right between the two pieces of our graph. And your graph is going to continue to get closer and closer and closer to that as we go out forever. So although this kind of looks like a horizontal line, it's going to continue to go towards that line, which is at a half, forever and ever and ever. It gets closer and closer and closer and closer the farther we go. Okay? So it really is continuing to move and not being a horizontal line. This will pass the horizontal line test. So take a second, look at your picture, understand what I'm telling you, and know that anytime it's a fraction, one of these rational expressions, it does pass the horizontal line test. Hard to see in the picture though, isn't it? Okay, but they will pass our horizontal line test. So then how do we go about finding our inverse? Step 2, after we decide that it has an inverse, is to flip our x's and y's. So I'm going to come over to the equation and change all my x's and y's. Well, that puts 2 y's in this equation, and that's where the solving for y gets a little bit more challenging in this one. So I'm going to put step by step off to the side as to what I'm doing to solve this, because guess what? It's never going to change. When you guys see these fraction ones, you're going to follow these same steps every time. The very first thing I do to attack this is just to multiply by the denominator so that I'm not working with a fraction anymore. So I'm going to take both sides and multiply by my denominator. Always. That's always the first thing I'm going to do when dealing with a fraction. Okay? In the same step, to just kind of consolidate how many things I have to do, I'm going to go ahead and distribute on the right-hand side as I go to this next step. Multiply the denominator and distribute. Okay, so that will give me 2yx minus x equals y. All right, ultimately, I need this to say y equals at the end. Well, in order to do that, I have to get all of my y's onto one side. So anything that has a y needs to go to the same side. Anything that does not have a y goes to the other side. Okay, so we're basically splitting by y's and not y's. So I'm going to move everything, my y's to the right-hand side, but get your y's on the same side. Okay, so I'm going to subtract the 2yx over to that right-hand side. So at this point, one side should have no y's, the other side, everything should have a y. The side where everything has a y, your next step is to factor out that GCF. So they all have a GCF of y, and I'm going to pull that out to the front. Okay, so my GCF that I want to factor out at this point is y. When I factor a y out, there should be still two terms left, something minus something. Well, this first one, if I factor y out, all that's left over is 1. Don't forget that there's still something there. Minus the second term, if I factor a y out of that, is just 2x. Our final step is just to divide by what was left over when we factored out our GCF. Okay, so divide to get y alone. And so I would divide by the 1 minus 2x. Always with these problems, any problem we ever do, I check to say, is it a fraction, is it a radical in the bottom of my fraction? This is a fraction, and so we would use our domain restriction for a fraction, and that says that 1 minus 2x cannot equal 0. Our denominator cannot equal 0. Solve for x. X cannot equal 1/2. So this is our inverse function as long as x does not equal 1/2. Now, the other thing I want to point out on this one is this. When you're doing these, we could have gone the other direction up here. I could have moved my y's over to the left-hand side and moved my x to the right-hand side. If I had done that, it would have just switched the sign on everything. So in the fraction ones, if you get to the end and you have all of the same numbers, like an x, a 1, and a 2x, but all of your signs are exactly opposite, maybe you have a positive, a negative, and a positive, guys, you have the right answer, okay? As long as your numbers are correct, if your signs are exactly opposite, you're fine, because all that's happening is you simplified out the negative that's there, okay? And that's okay. The other thing I want to point out is, on this one, if I did that, our inverse is the exact same thing as our original function. And that happens sometimes. Sometimes, and that is if I were to draw in that y equals x line, and it flips over it and matches exactly up with itself, it's its own inverse, okay? And that doesn't always happen, because that didn't happen on this one, right? So you don't always get the same function, but you can. It's not like you did something wrong if that happens. Any questions on that? Okay, the last little part of this is verifying inverses. Sometimes they're going to start out by just doing the work for us and saying, here's the original function, this is its inverse. Prove it. Okay, that's that whole algebraically confirming. Go back to geometry, proofs. You got to go through the steps to prove it. And this is how we do that, is that we can use the composition of inverse functions to prove that they really are inverses of each other. If they are inverses of each other, if I do the composition f of g, and I clean it up, it will clean up to a plain old 1x. And then if I do the composition g of x, it will also clean up to equal plain old 1x. And that's how I verify. And so this is similar to our algebraic confirmation of things like symmetry or odd or even. You must show the setup. You must show the work, which will be 1, maybe 2 lines. And then you must show that it equals x. Those are kind of the key things that we hit along the way. So let's look at an example of this. They tell us that these are inverses. That's not the question. They say these are inverses, verify it, okay? So our verification is a two-step process, f of g and then g of f. So f of g, I go ahead and set this up. Here's f. Wherever there was an x in f, I'm going to plug g into that. Okay? Now, if I'm good at my algebra, this next part is really easy. It doesn't usually take very many steps, but I have to do this in the correct algebraic order. Okay? Can I start out on this one multiplying 2/3 times 3/2? Is that a legal maneuver in this one? Yeah, I can do that. Okay? What is 2/3 times 3/2? 1. So I don't need to show this, but this is the part we're doing right now, and it comes out to equal 1. And so I don't need to write 1 anymore. All that I have left is x minus 2 plus 2. Well, then I can combine my like terms. Minus 2 plus 2 is 0. It's gone. And I am left with x. So notice how much work that took me. Set up. One line of doing the correct algebra. Answer is x. Answer is always x. That's never going to change. Do g of f. Okay, this is where we have to remember our algebra. On this one, is it technically legal for me to do 3/2 times 2/3 first? No, that I can't do. So on this one, I would start by doing my combining of like terms in there and do the plus 2 minus 2 first. So we would be left with 3/2 times 2/3x, and plus 2 minus 2 is gone. And now 3/2 times 2/3 is 1x. So we just have to remember our correct steps. And there's sometimes some options up there, but make sure that you're doing things in the correct, please excuse my dear Aunt Sally, order, right? Cleaning up our equation there. Questions on that? All right, you try one. On your own, given f of x equals x squared minus 2 and g of x equals square root of x plus 2, do f of g and g of f. Show the setup, clean up, equals x. Okay, so cleaning this one up, there's my setup. Correct steps that I should show algebraically. Squaring and square rooting are opposites, which would leave me with x plus 2 minus 2. Plus 2 minus 2 is 0, leaves me with equals x. Over here, I should combine my like terms first, which gives me square root of x squared. Squaring and square rooting is our opposite. I get left with x. I will tell you right now that for whatever reason, this is the one that when we get to our test, people forget. Go back and look at how do I verify that they are inverses. F of g, g of f, they equal x. Your assignment tonight is on page 70, 2 through 18 evens, 28, and 30 through 32.